Good morning, everyone. So here in this particular session, we will be discussing about the lab programs here with respect to your Unix and operating system lab. So, but before discussing some programs related to this particular Unix and operating system, I just wanted to explain you people the different programs what we are going to learn in this particular session. So the very first thing, as you can see, what exactly it is written here is Unix operating system lab. So it is not only a operating system lab, it is actually a combination of two different type of operating systems. So here we do have something called as Unix. So Unix is a one kind of operating system what we have, and another operating system means nothing but you can consider it as Windows and other kind of things. Basically, we are going to discuss about Unix operating system. So means all the programs what we are going to write here that should be actually executed in Unix operating system. But since many of you might not be having Unix operating system, they most of them might be having I think Windows X version that may be 7, 8, 10, etc. Right? So we will be executing the what we call the normal program. The operating system programs will be executing in Windows. You can directly execute in Windows as well as in Unix. So I will explain in the next session related to how to execute the programs in Unix and what are how the commands can be executed. Since I have to install it using some, I told you that we have to use some workstations and we have to install in that. Okay, virtual firmware we do have. Within that we are going to install operating system. Means within your Windows operating system you can install Linux and you can run both the operating system in your system without removing Windows operating system. So that is the best part of this particular work. I'll tell you how to do that, but not today. Today, since we can write the programs normally using this C++ or something like the C++ or Turbo C, so we will see the programs which we can write directly in this particular concept. So the first thing is all about here. I'll just provide you the syllabus. Now there are some modifications. If you see here, the first few programs are related to something called as Unix. This can be executed only in Unix platform. In Windows, we cannot execute it. That is nothing but a study of Unix by Linux general property utility commands. Utility commands are nothing but, as I told you that, for example, if I want to open any application in my Windows operating system with the help of a mouse, I'm going to click on that particular folder or the application, and I'm going to start executing it. But if you talk about Unix or Linux operating system, there we cannot do it. Earlier, we don't have GUI based interface. We used to have only commands, and using that commands only, you can try to get the entire information. Same way here also we do have in Unix, we have these commands, something man command, who, cat, cd, cp, ps, ls. All these commands we have to execute in our operating system, that is Linux. I'll explain them. These are very easy commands and you people can perform it very easily. Okay. So I'll explain them when we are discussing it. Then we have something called VI editor. Sorry. So like in Windows, if you wanted to write any program, normally, for example, if you are using some area, what we call Turbo C in order to write the program. So what you are going to do in the beginning, you will be opening a editor, right? You will open an editor. That is what we call it as Turbo C editor. And that will comes in a blue screen, and there you will be writing the program, saving it with .c extension, then compiling it, and then executing that particular program. So not only that, if you don't have this particular editor, you can directly write programs in a notepad, right? We can also write programs in notepad, C programs, and we can store that particular program in a with a .c extension, and then we can directly execute in this particular editor, right? Same way here in coming to the Linux also, we are having an editor. We call it as a VI editor. So in this editor, you people can write different programs and you people can execute them. And then we have something called study of Bash shell, Bourne shell, and C shell in Unix and Linux operating system. So here, these are the different kind of shells what we are going to use in Linux in order to write different programs and execute them. And then we'll discuss about study of Unix or Linux file system. So how it is arranged? Like Linux is not only Linux, even your Windows is actually systematically organized in a format of tree structures. As I told you that you people might have created a folder called as movie, and now this particular folder you have categorized based upon specification, that is nothing but language. For example, Hindi, Telugu, English, some people like Kannada, so on. Okay, now here if you talk about let's go further, and if I talk about English movies, again you are further subdividing that into different categories, something like thriller. Then we have something like called as romantic. Then you have something called action. Then we have something called adventure, so on. So what happened here? Now this is the way how internally your system is going to organize your entire files. Same way the concept is used in Windows, and the same way it will be used in Linux. So whatever the files we people usually create, we randomly might be creating it, but system will keep a track of each and everything. Now you can call this as a root file. This is what we call it as a root file. So using this file, this is a main file, so we call that as a root file. So whenever you want to access any of the file, for example, I want to access action from English, this, so I need to give this particular path. What is the path here? Slash movie slash English slash and then action, and within that action I'll be having a movie, something like xyz dot mp4. This is a basic path. So if you know this path, then only you can open that particular folder and start playing that particular thing. So how it is exactly arranged, that we are going to see in this particular concept. Okay, so these are very easy topics, very small. Directly I'll give you the data related to that. You people can just write it up, and then I'll tell you how to execute it so that you can easily execute it. Next, we have something like a C program that makes a copy of a file. So you people know how to copy one file to another file. You people might have written this particular program in your C language. Same program we are going to write, but this time we are going to write in something like we call Linux platform. Okay, so Linux operating system will be writing a C language for copying one file to another file using system calls. So I think you basically know what kind of system calls we use in order to copy from one to another. Then we have to emulate a Unix ls underscore l command. So what do you mean by ls command? I'll tell you. Actually, the ls is nothing but listing. For example, as I told you, in an action folder, you may be having some 50 copies of different movies. 50 copies of different movies. So all these movies will be represented. So that all movies will be represented. So when you are present in this particular folder action, you can simply type ls, whatever the files and folders present in this action file will be displayed. That is what we have to do it using program. So using program, we are going to display that particular thing from one of the particular folder. Then we have some C program to illustrate how to execute two commands congruently within a command. So how we can execute ls underscore l command and sort command simultaneously, that we will see. Okay. So if you talk about these four programs, these will be executed purely in a Linux programming. We cannot execute them in a Windows program, operating system. These are purely based on Linux. So we need to execute them in Linux only, these four programs. After that, whatever the programs are there, this we can execute normally in Windows too. Let me show you. Yeah. So the first program what we have here is something simulating the following CPU scheduling algorithm. So it's asking you to simulate the scheduling algorithm, something like round robin. I think you people have watched the videos and you people have a clear clarity related to round robin, SJF, FCFS, and priority. And today we are going to see that. And if you don't have that particular clarity, I just ask you people to please watch those videos so that you can get clarity how this particular scheduling algorithm works. These are important as per your main exam point of view, as per internals, as well as for your scoring for India labs also. Okay, these are very, very easy programs what we do have. So round robin, SJF, FCFS, and priority. So today we are going to discuss this. Along with that, we are going to discuss about something called multi-programming memory management implementation. So these are the system calls we have: fork, wait, exec, exit system. Well, this is another program where we can execute in Linux only. This is another program what we are going to execute in Linux, but this is one of the easiest program what we do have, hardly some 5 or 6 lines of code. 6 lines of code what we do have in this particular scenario. So this can be executed but only in Linux programming, and the remaining all we can execute in something like what we call in Windows itself. So yeah. So the next program what we have is simulating the following: MVT, MFT, and MUT. That is nothing but multi-programming with fixed number of tasks, multi-programming with variable number of tasks. So if we have some random variable, random task, okay, some set of tasks, how we can execute them? That is for that we are going to do this particular programming and all. And this is for fixed means we have some fixed set. This I'll explain it. This concept will be coming in a third unit, and then we'll explaining, and then we'll do that. Then we have something called as Banker's algorithm here. This is related to deadlock. These two programs, whatever you people are saying, these are related to deadlock concept. And if I'm not wrong, you will be getting this in your fourth unit, I guess. In fourth unit, you are having deadlocks. Okay. And next we have something called FIFO, LRE, and LFU. This is related to your page replacements. Page replacement techniques. So what I mean by page replacement here is something in the memory. This is, for example, this is your some portion is given for the operating system, and the remaining free space, whatever you're seeing this one, here we will be loading the pages. Whatever the application you wanted to run, that pages will be loaded here and it will be executed. It. So once that application is completing the work, and then we have to remove it and we have to bring in a new particular program, then we will be what we are going to do, we'll simply remove that particular page and we'll bring back the new page for its execution. That I will explain them, okay, and after that you'll get a clear idea, then we'll be going ahead with this particular programs. And next we have something called sequenced, indexed, and linked. These are also related to files. As I told you that the information will be stored in files hierarchy. So how these hierarchy we can access it? Sorry, how we can assess this particular, we have different strategies using which we can hire these particular programs. So that is what he's talking about here: sequence, indexed, and linked. And if you talk about the 12th and 13th program, this is related, these are very interesting, and these are related to what we are discussing now. Something we were discussing about synchronization. I don't know how many of you are watching my videos. If not, please request you people to watch the video so that you can get a clarity. Then only you people can understand these particular programs. So in this we have something like shared memory. So this will be coming already. I think we might have completed. This comes in inter-process communication. Inter-process communication. So in inter-process communication, we will be using shared memory. And whereas coming to first and all, this we will be using for synchronization purpose. So these two are very, very important topics and very, very important too. These are newly added for your people. R30, R16 regulation doesn't have this. For R19, they have added, included. So last four, that is 12, 13, and just 14 and 15 are extra programs that have been allocated to you people. But these are very, very easy and interesting too. C program to create a thread. So here I think you people having a Java, and in Java, so might be explaining, might have explained it or might be explaining something called as threads or main purpose threads. So that threads we are going to use in order to write a program. Okay, so here he is talking about P threads. You might be watching wondering what is P threads. P is nothing but here POSIX. We basically call it as POSIX threads. So what is the main purpose of this POSIX threads is nothing but these are the threads used in Unix. Like we have something, you people might be using threads in Java. We call it as J threads, Java threads. Same way, these are what we call it as POSIX threads. So P thread are nothing but POSIX threads, which are used for execution purpose. Okay, execution of multiple tasks simultaneously. But these will be run in a POSIX command. So definitely you have to write this program in Linux. Same way, we will be using pthread library for executing multiple. So threads are used. What did I say? Threads are used for execution of multiple tasks. For example, let me explain it. Let us suppose you have created one process. Now that process is internally creating some sub processes like this. Now these processes are again creating some sub processes for their task to get completed. Okay. Now what happens here? If a process, if this is a main process which is creating sub process, and each sub process is again creating sub processes, what will happen here is we can call this as a parent process, and this becomes a child process. But when you consider this portion, This P4 will be acting as a parent, and this will be acting as the child process. This is a way. But the problem here is that if these processes are going to keep on creating sub processes, the burden on the system will be high. The burden on our operating system will be high. The impact will be very high. The system may get slowed down. The system may start hanging up. That's a problem. So here, what is the alternative? What we can do here is we can use threads. So what happens here is in this particular thing, here the parent, I mean the main process will be creating the sub processes. Now this particular process, rather than creating 4 different processes here, it will create 4 threads. See, like this. So it is going to create 4 different threads. And we know that what is thread is nothing but it is a lightweight process. Lightweight process. So this particular thread, what it is going to do, it will simply execute the task and it will return the information and it will come back to the process. So we don't, if a particular process P1 is creating another process P11, we need to allocate a space for this either 15 or 70. But if you create a 3 thread here, the thread will be accessing the space from the P1 itself. And once it completes the task, it will again give that particular space back to the P1 automatically. Means it will return back to P1. If another task has to be executed by P1, then again this particular thread will be used. These threads will be used for execution purpose and it will come up. That's why it is called as lightweight process. You will get a clear picture when in Java class the sir might be sir will be explaining you paper. Then you will get a much more idea related to that. So on the threads itself, you people had to write 2 different programs here. That is something like pthread libraries, and then we have something like congruent execution. So multiple using multiple threads, how you people can execute multiple programs. That we are going to see in the 14th and 15th program. So today we will try to cover this particular program, something like where it is. The 5th program we'll try to cover, and the 6th program I will explain it. Later I'll show you the working of this because I need to install Linux in my system. Okay, using workstation, and then only I can show you up. So for time being, this one and the first portion we'll keep it on hold. So today we'll discuss about the 5th program, that is nothing but the process scheduling algorithms, round robin, SJF, FCS, and priority. Okay, without wasting time, first I'll explain here itself, and then we'll go ahead with this. Yeah, this is the program what we do have. The program. So as per our 16 point of view, this is the first program, but for you people, he has clubbed it up. So this will be a 5th program. So here I have given the explanation related. So I think you people have a clear idea what they mean by FCFS. So in FCFS, what we are going to do, so if multiple processes are coming for execution, whichever process comes first, that process will be allocating first to the CPU. Okay, and that particular CPU will start executing. So when this process completes execution and comes out of CPU, then the next process will be allocated. This is something like, you people are going to a hotel for having a nice dinner or a brunch. Okay, so there what happens, the come first basis, he will be allocating you the table. So whoever comes first, they will be allocated the first table. Then whoever is coming second table, third. So if there are only 10 tables are there, so when the 11th person is coming, he has to wait if there are no tables available. If all the 1 to 10 are filled, occupied, then the 11th family, whichever is coming, has to wait until one of the table gets freed up. Let us suppose after some time the 5th table has been released by the 5th family, whichever it is. Now the 11th person will be allocated that particular 5th table. Okay, if the 12th person is in already in hand, he will not be allocated first. Only the 11th person will be allocated, and after that, if any other table is available, then it will be allocated to the 12th person. So that is the simplest scheduling algorithm what we have. So here, whatever might be the problem or whatever might be the thing, we are not concerned. Means whether the person is sitting for 10 minutes. Suppose the 11th family, whichever, oh, sorry, the 12th family, whichever is coming, he will be sitting there only for 5 minutes, not more than that. He just came to have a cup of tea, let us suppose, and the 11th person is coming here to have a dinner. So dinner means definitely it will take some 1 hour, half an hour to 1 hour of time. But whereas coming to the 12th person, he requires only for 5 minutes. But in FCFS, the problem is since 11th person has family has come up earlier compared to the 12th family. So this should be allocated. Now, when we are allocating this to a table, let us suppose the fifth table is the only table we are available. Now, until these people are completing their lunch, we cannot allocate to this much. How much time this particular 12th family has to wait here? So something like 1 hour, 5 minutes to complete the task. So that's a problem here. So this is the main drawback of this FCFS scheduling. So in the video, I have explained it perfectly. I think you people might have gone through it. Okay, so based on that, we are going to see here. So if you see here, if you're talking about turbo C programming, if you're writing it up, then we are going to use this particular command, something like hash include conny.h. But in case if you're writing this in dev C++, you don't require this header file, because this header file will consist of program. I mean, what we call the logics related to clear string and the logics that are related to get ch. For these two, this particular thing is going to take place. Okay, since in dev C++ both the commands we are not going to use, you don't have to write this one. So I am giving it as per turbo C point of view. If you're executing the programs in dev C++, make sure you're not writing this particular header file. So only one header file we require as a standard input output header file. Now, so in now we will be using some declarations here. So we are going to initialize some int bt. Bt is nothing but here. What is the main purpose of this FCFS scheduling algorithm is we wanted to determine the waiting time of a process, individual process, then the average waiting time of a process. Same way the turnaround time of a process, then the average turnaround time of a particular process. This is what we need to discuss here. So int BT20, so BT is nothing but the burst time. So every program will be given a burst time. Okay, P1, P2, P3, 24, 3, 3. This is the burst time. What I mean by burst time is nothing but how much time this particular process is going to use the CPU. 24 is nothing but the burst time. What I mean by 24 here is nothing but for 24 milliseconds, this process will be occupying the CPU for completion of the work, whatever is assigned to the P1. Same way if we talk about P2, we have 3. What I mean by 3 is nothing but 3 milliseconds. For 3 milliseconds, the process P2 will be executing this particular program. If we talk about P3 here, it is executing suppose 3 milliseconds. So it is going to, the process P3 is going to occupy 3 milliseconds of CPU for completing its task. That is what we call it as burst time. Now, since I told you that we are going to calculate the waiting time here of a individual processes and the average waiting time. So here WT is nothing but your waiting time. Then we have something called as turnaround time. And I and n are the variables we are going to use in our program. So since we are going to calculate the average waiting time and average turnaround time, we have average waiting time, average turnaround time. These variables you people can declare as per your convenience. It's not necessary to use the same thing. Now, what we are going to do here is, okay, the small mistake, printf enter the number of processes. Okay, this is something w, this is not w, e. So enter the number of processes. So I wanted to first give or take how many processes I want to come. I mean, so within a system, how many processes are going to come, and based on that I'll be taking up the burst time. As I told you that every process will have a burst time. This is process, this is burst time. So what do you mean burst time here is nothing but 24. So p1 is going to take 24 milliseconds. So remember, this will be in milliseconds. If he is not giving the extension, the parameters here, you can consider it as a units, 24 units. So but by default, you can use it as 24 milliseconds. In exam, if he's not giving anything like in milliseconds or something like that, you can consider it as 24 units. So the burst time for the process, and then I'm going to take. So every process I'm going to take the burst time. So initially the waiting time will be 0, average waiting time will be 0, turnaround time and average turnaround time I'm giving it as okay, because we did not execute anything, so we don't have anything like that. So next what we are going to come across here in this particular thing is, so we will be calculating the waiting and waiting time here. So simply for I equal to 1, I less than n, I plus plus, we'll be performing the waiting and turnaround time and the average waiting and average turnaround time. So as I have explained in the video that we can prepare a Gantt chart here. Okay, first let me see what I have given is 24, 3, 3. Cool. Now explain it. So if you want to tally whether the output whatever you're getting is correct or not, I already explained in the video that how to use Gantt chart. So let us suppose I'm taking total 3 processes. Okay, better I will explain using a board here. Yeah. So let us suppose we are taking a 3 processes P1, P2, P3. P1 consists or it requires 24. This is your burst time. Okay, this is the process P. So initially the waiting time will be 0. The turnaround time of all the processes, since we are talking about all the process, 3 processes are there here, right? So we will be using an array. So waiting time of n processes is, so here 3 processes. So waiting time of all the 3 is 0. Burst time of 3 will be 0 initially. So burst, sorry, not burst time, waiting time and turnaround time of this process will be 0. Madam, printer కావాలి అక్కడ తర్వాత ఇస్తాను అంటే ప్రింటర్ తీస్తున్నాం ఇక్కడ తీసి ఇచ్చేస్తాను మీకు ఇచ్చి మళ్ళీ ఇబ్బంది కదా అది తీసి ఇచ్చేస్తాను yeah 24 okay so next is 3 so initially the waiting time turnaround time everything is fine so how we can determine what is the waiting time of a process p1 and this we can do it with the help of a Gantt chart. I think you people are familiar with it. Gantt chart. So in this, what we are going to do, first we will draw a graph like this. Since I did not give any waiting time, if you remember here, I did not give something like arrival time. Did I provide any arrival time here? No, I just provided you with the burst time. So what does that mean? That all the processes P1, P2 and P3 has arrived at the time interval 0. Means at 0 milliseconds, all the 3 processes have come up here. From 0 it is going to start. So all the 3 processes have come up at 0 milliseconds. This is what I just wanted to explain you people when you are solving it. The same also we are going to use it here. I'll explain it. So initially 0 milliseconds. So since all the processes arrived at 0 milliseconds, we will start from 0. Initially we had to start from 0 only whenever we are starting it. So what is the first come first serve? What is the first process we are coming here is P1. So we will be allocating process P1 here. Now how much time I have allocated to this? How much time this particular process required? 24 milliseconds. So from here to here, 24. So 24 milliseconds. So this much amount of time, 24 milliseconds of time is required by the process P1 for execution purpose. And once it completes executing in within the CPU, it will come out and then we will be allocating another process. What is the next process we have in the queue? P2. So what is the P2 will be allocated? Now, how much time it requires to complete the entire task? 3 milliseconds. So 24, this will be 27. Remember this gap. Whatever the gap you people are showing, based upon the values given, you should show the gap. You can see that 3 milliseconds is very less when compared to 24. So we have given more gap for P1. Then we have given a small 3 milliseconds gap for P2. Then we have another process P3 that is 3 milliseconds P3. So I'll here 27 plus 3. How much we are going to get is 30 milliseconds. I hope it's very clear how we have drawn it. I'll explain it one more. So since we have process P1 is required 24 milliseconds and all the process has arrived at 0 milliseconds, we have started from P1. For the P1, we have allocated 24, 0. We have started at 0 milliseconds, so 24 milliseconds are taken by the process P1 and it has completed execution. Once it came out, then process P2 came into picture and this process requires how many 3 milliseconds of task. So we have allocated process P2. So 3 milliseconds. Now here it is 3 milliseconds. So 24 plus 3 is 27. Then again the process P3 came, it requires 3 milliseconds. So 27 plus 3 is 30. Now if I ask you what is the waiting of process P1? Can anyone tell me? Well, I guess it is something like if I ask you what is the waiting time of a process P1, how to identify it is yes, exercise. So if you are using Gantt chart and trying to do it up, it's very easy. Simply what you have to do is you have to just see the leftmost of that particular process. P1 leftmost is 0. So waiting time for the process P1 is 0 milliseconds. If I talk about waiting time of process P2. So what is the waiting time of the process P2 here? So leftmost, whatever it is we are having, this one 24. So we can directly write it as 24 milliseconds. That is a waiting time. And then waiting time of process was P3. Leftmost is 27. So 27 milliseconds. Come here. So what is the average waiting time if people are going to get average waiting time? So this is nothing but 0 plus 24 plus 27 by 3. Since there are three processes, so how much we are going to get here is something like let's take a calci, then I'll explain it. Okay, 24 plus 27, 51 by 3. So it is 17, right? So how much we got here is 17 milliseconds. Same way we are going to do it for turnaround time. It's also very easy. Let me explain. Let me erase this. So if we talk about here turnaround, let's take the turnaround. So the TAT of process P1 is how much? So for TAT, the simple logic what you have to use here is the right side of that particular process, what it is, we have to consider it. So what is the process we have here? P1. Right side, what we have? 24. So 24 milliseconds is the turnaround time, the total time taken to execute a particular program. Then we have turnaround time of process P2 here. So if we talk about P2, where it is P2, here it is. So right side what we have 27. So the turnaround time for this particular thing process P2 is 27 milliseconds. Then turnaround time of process P3. So what do you mean by turnaround time here is nothing but the total time taken to execute right from beginning, from the waiting time to the total completion of a particular task by that process. So P2. So that is nothing but P3 is right side what we having value is 30 milliseconds. Now what is the average now? Average turnaround time of a process equal to 24, 27 plus 30 by 3. So how much it is going to be? See, 24 plus 27 plus 30 by 3. 81 by 3. So that is around some 27 milliseconds. I hope it's very clear with this. You people might have understood how to identify. This is where how you have to do it in your exam. But if you talk about a programming point of view, we can't do it like this because this is just an assumption. I told you that if you want to get the processing waiting time of a process, go to the left and see whatever is there. And if you want to get the turnaround time, go to the right and you can do it. But if you talk about programming point of view, you can't do that left and right concept here because we don't have anything like Gantt chart. This we have drawn it, but in the program we don't have anything like that. So definitely we need some logic here. So what is the logic we require here? And that's what been explained here in this particular thing. Okay, wait, let me add a additional page here. Cool. So here, what is the logic we are going to use is if you're doing the turnaround, so waiting time your requirements, waiting time of a previous, so waiting time of a particular process pi is equal to, okay, let me write it here, waiting time of a process pi of a particular process pi you want to determine. So waiting time of a process previous process I minus 1 is nothing but the previous process plus the burst time of the previous process. That is what we are going to do it here. So what is, suppose if I want to determine the process for P1. So what is the waiting time for the process P0 plus the burst time for the process P0. So I wanted to determine the waiting time of a process P1. So how we can write here is the waiting time for the process I minus 1. So P1 I want to do. So what is the waiting time of the process P0 plus the burst time of a process P0? That will give you the waiting time. Then what about the turnaround time? Same thing. The turnaround time of a process P1 is equal to how much? Is nothing but the turnaround time of the process previous process I minus 1. That is nothing but P0 plus the waiting time of a process P1. How much time this process is waiting plus the turnaround time. So this is the logic what you have to use in this particular scenario. And remember, this is in a loop we are doing. Same way the average waiting average is how much we have to do. This is the way how we are going to determine this particular waiting average too. So you can see here, I did not. So what I have did here is nothing but I simply added the values. In the sense, just I'll show you here. You're doing what I'm doing here 24 plus 27 plus 30. This is the thing what I am doing it here. 24. So here this what you are saying here. This is what you are saying. I'm simply adding those values. So if we talk about this one, well, how much value we have? 0 plus 24 plus 27 for waiting time. Average waiting time. So this is what I'm doing. So 24 plus 0 plus 24 plus 27 I'm doing here. And if you talk about the turnaround time here, 24 plus 27 plus 30. And this is what I'm doing it here. 24 plus here there. Since it is in a loop now. So in the first loop, the value for this will be 24. Here it will be 24. Again, when the loop will be running, so three processes we have used now. So again, next process when it is coming, 24 plus 27 plus 30. So you might be wondering, sir, where, but we did something like 24 plus 27 plus 30 by 3. That by 3 I'm doing here when I'm trying to print that particular statement. Here I'm just doing this 24 plus 27 plus 30. And if you talk about the waiting time here, average waiting time here, what I'm doing is 0 plus 24 plus 27. But actually what we need to do 0 plus 24 plus 27 by 3. So whatever the value we got 17 milliseconds, something like that, something, and that will be. So here I'm doing this. See, waiting average by n. How many process? By 3. So this by 3 I'm doing it here. Turnaround time average by n. So here I'm getting the turnaround time variables, that is 24 plus 27 plus 30, that is something 81. So here I'm doing 81 by 3. I'll get the value whatever it is. So this is the way how this particular logic has been written. It's very easy. So you can see here, enter the number of processes 3. I'm giving 3 processes here. So the first process is 2433. So I'm printing the process. The process will be P0, P1, P2. Burst time is 2433. Now what is the waiting time we have got? 0, 24, 7. Now you can cross verify it. So we got the waiting time as 0, 24, 7. So you got the output as correct. And then what the turnaround time we got? 24, 27, 30, right? So 24, 27, 30. So this is what the turnaround time for the processes we have got it. So this is also correct. Now what is the average waiting time we got here? So if you see here, average waiting time of process is 17 milliseconds. So you got 17 milliseconds here, and then we have 27 milliseconds for the average turnaround time. So the average turnaround time for the process, how much we got here is 27. So your answer is correct. This is the way how you people can rectify it, and how you have to cross check whether the program's outcome, whatever it is coming, is correct or wrong. Now I'll show you practically executing this. Now this is the entire program what we have written. So the burst we can give it for 20. What is the total I have given is 20 here. So what does that mean? That 20 processes can be taken simultaneously and it can be used for execution purpose at a time. So I have taken only 3 processes. So burst time will be BT of 3. It will be something like here it will be like burst time of 3. So I'm using only 3 processes, but remaining 17 memory spaces will be empty because I have allocated a memory space for 20 processes here. Okay, but I'm using 3. Now it's up to you people. You can just go through different websites, try to get the problems and try to solve it using this particular program. So as I told you, enter the bus time. Sorry. So you can see here on the answer. Okay, here it is wrong, right? Let me modify it. Okay. Let me modify this. This is something we wanted to give enter. So I'll just save it up. I've saved it. Now let's see. Processes, and this is the formula, this is the logic, this is a logic what is important in order to execute. This is what you should understand here. And after that, printing the statement process, burst time, waiting time, and turnaround time. And since I equals 0, I less than n, I plus plus, so I'm going to perform the determine the average. So here I'm just printing the burst time, the waiting time, and turnaround time. From where we are going to get it is here. Waiting time, turnaround time. Burst time you will be getting it from here, this one. From here you will be getting that information. Okay, so now we are going to print the average waiting time here, the average turnaround time. This is how we are going to give it up. So let me execute and show you the output, whether we got the same output or not. F11. Fine, you got the window here. So here, how many processes we gave here is 3 processes. Yeah, so the burst time for the first process is 24. And the next process is something we have given it as 23, I guess, 3. And the third process we gave it as 3. Now you can see here clearly that the burst time for the process is 24. So the waiting time, okay. So the burst time for the process P1 is 3 and the burst time for the process P2 is 3. So what is the waiting time we got here is 0, 24, 27. And the turnaround time is 27, 24, 27, 30. That is what we have got it here, I think. Yeah, 24, 27, 30, 0, 24, 27. So it is very clear. Now the average waiting time what we got here is 17 and this. So let's see here how much time it has actually taken your process. See, even you people are executing a program. I told you that a program under execution is what we call it as a process. You, if you don't remember, if you're saying that what is the proof for that, you can see the proof here. What it is written here, process exited after 25.2 seconds, means even whatever the program you have written here, once you start compiling it, that program has converted into a process. Now that became one application and that application executed it, and it has given you this particular window, and within this window you have executed some task. That is what we call it as process. Even your program is acting as a process right now. So if you see here, it has taken only 25.2 seconds time in order to return the information whatever it is. Okay, I hope it's very clear till here. So this is the way how you people have to execute, and press any key, you'll be coming back to your previous session. It's very clear till here, I guess. This is what comes under FCFS. The very next one, what we have here is SJ. The next one, what we have is shortest job first. What exactly we are going to do it in this particular thing? Okay, first let us take an output and let me explain it. So 6873. So 4 processes I am taking it. Okay. Now let me take a board here. So here what we are going to do is I'm taking 4 processes here. This is your process. This is the burst time. What we are doing here is a non-primitive. What we are doing here. So we have 4 processes: P1, P2, P3, P4. So if we talk about P1 here, the process P1, we are getting how much value he has given here is something like what he has given 6873. Okay, so here it is 6873. Okay, so what is the burst time is 6 milliseconds for the process P1, 8 milliseconds for the process P2, 7 milliseconds for process P3, and 3 milliseconds for the process P4. Now, in SJF, what we are going to do is we will not give or allocate the process as FCFS, first come first serve. The one which is having the shortest time, that will be allocated. Since I told you in the previous example that we went to a restaurant, that we got a one family which requires 1 hour time to complete the task. We have another family which requires only 5 minutes to complete the task. So earlier in FCFS, okay, since the first family has come up first, we will be giving that particular means the table to that particular family. But here in SGF, not like that. Here they will determine how much time you're going to spend. So since this family is going to spend only for 5 minutes of time, this particular family will be allocated at the table first, and this particular family has to wait. That is the simple logic for this SJF. So let's draw the Gantt chart and let me explain it how it is going to work out here. So remember that all these I did not give again arrival time for all the processes. So all the arrival time for all the processes here is 0 milliseconds. So I'm going to start from 0. So we have four processes P1, P2, P3, P4. Among this, which is the shortest burst time we have here? You can see that 3 milliseconds is shortest. So we will be allocating process P4 first. Okay. So when we are allocating how much time it requires 3. So 0 to something here. 0 plus 3 is 3 milliseconds. So this task is completed. Next 6, 8, 7, which is the shortest 6. So I will be allocating the process P1 first. So 6. So how much time it requires 6. So 6 plus 3 is 9. So 6 is much more bigger than this. I'm giving more space here. Sorry, 9. And after this 6 plus 3, 9 completed. 8, 7, which is shortest? P3. So P3. So 9 plus 7, 16, I guess. Yes, 16. So somewhere here it will come as 16. Now we have 8 here, right? 9, 10. Yeah. Next we have something. The last one is P2. So P2 requires how much? 8 here. So 8. So 16 plus 8 is 8, 9, 10, 11, 12, 13, 14. So it will be something here. I'm giving it as 24. Okay. This become a little shorter. So make it till here. So this is 24. Okay, so now you people have got the Gantt chart here. Now we will try to find the waiting time here. So let's see the waiting time. So the waiting time of process P4, sorry, P1. So if you see here, the P1 is executing here. The left side, what we have 3. So 3 milliseconds. Now the waiting time of the process P2, how much we have here? Left side is 16. So it is 16 milliseconds. So the waiting time of process P2, P3, how much we have P3 here? 0.9 milliseconds. Waiting time of a process P4 is equal to how much? 0 milliseconds. But one thing I want to make it clear here is, in case if the arrival time is different for different process, for example, since all the process has arrived at arrival time 0, I am simply writing whatever the leftmost is there. That is 3 milliseconds for the process P2, 16 milliseconds for the process P3, 9. But in case he has given something like this, arrival time for the process is 0 milliseconds. Let us suppose. Sorry. Okay, yeah. For the process, the arrival time is 1 millisecond. Let us suppose here the process for arrival time for the process is 1 millisecond, for the process P2 is 2 milliseconds, like that. Then what you have to do here is 3 minus arrival time. What is arrival time here we have for process 1? Then it will become 2 milliseconds. You're getting it? I hope you're getting it. If the arrival time is different for different process, you have to subtract the arrival time too. Actual logic is whatever the leftmost side I'm telling for the waiting time, whatever the leftmost side you're having it, this one 3 minus arrival time for the process P1. How much we have? 1. So 3 minus 1. So the waiting time for the process is 2 milliseconds. But since I am telling that here in this particular scenario, the arrival time for all the processes 0 milliseconds, right? So that's the reason I'm simply writing 3, because 3 minus 0, actually I had to do something 3 minus 0. So that is 3 milliseconds, because all the processes arrived at 0 milliseconds. So what is the waiting time for the process P2 here? 16 minus arrival time. So it came at 0 milliseconds. So 16 milliseconds. So it came at 9 millisecond. Now the process P3 has come up at 9 millisecond, but arrival time is 0. So 9 minus 0, so 9 millisecond. That's the reason I haven't explained while during in the video too. I did not mention this arrival time, because all have arrived at 0 milliseconds. We can directly write it. But since if the values are different, like as I told you, P1, P2, P3 like that, then we have to subtract it. But in our scenario, it is 0 milliseconds. As I am writing it, 0 minus 0 is 0 milliseconds. This is the way how we are actually doing it. Okay, remember, I please remember this. If the arrival time is given within the particular code, then you have to subtract that particular arrival time from that particular waiting time of a process. Simple logic is P1, left side whatever we are written, we'll write it minus arrival time for that particular process. It's like it is 1 millisecond. So 3 minus 1, this will become 2 milliseconds like that. But in this case, we are not doing that. So I'm just eliminating this. So with the help of this, I think you people might have understood. So you people had to calculate something called as average waiting time here. So average 3 plus 16 plus 9 plus 0 by how many processes? 4. 1, 2, 3, 4. 4 processes. So how much? So how much we are going to get? So it's something like 3 plus 16 plus 9 by 4. Okay, so we got something 7 milliseconds. Same way for the turnaround time. Now for the turnaround time, you don't have to calculate the arrival time here. Directly you can write the way I explained it. Turnaround time for the process P1, how much we have left side? I mean right side, 9 milliseconds. For the process P2, we have 24 milliseconds. For the process P3, it is 16 milliseconds. And the process P4, it is 3 milliseconds. So what is the average turnaround time we are going to get here? 9 plus 24 plus 16 plus 3 by 4. So how much it will be? So let me see it here. So 9 plus 24 plus 16 plus 3, 52 by 4, it's 13 milliseconds. So how much we are going to get here is 13 seconds. Okay, so let's see here the logic. So here is your FCFS program. This is the entire program. So you can see I have kept it in a comment, the CLR and get CH here. The first statements, first some 17 line of statements will be same here. So I have written here conya.h. Okay, so you can keep it in comments here. Save it. Remain process sim. Say enter the number of process scanf. So we'll scanning. So how many processes we have taken? 4 processes here. Then we are going to give the burst time. So for I equal to 0, I less than n, I plus plus is 0. So for example, 4 processes in the sense nothing but we are starting from 0. Process P0, right? P0, P1, P2, 3. How many processes? 1, 2, 3, 4 processes. So 0. So I equal to 0. I less than 4. So less than 4 means it will start from 0, 1, 2, 3. When it will come for 4, the condition will fail. So this is what's the value of n is 4. We have started from 0. So p of 0 is equal to how much? 0. So initially what we're doing, we are allocating for the process p0, we are allocating an id as 0. Then we are asking to enter the burst time for that particular process. That is nothing but 6, 7, 8, 3 something we have written it, right? That is what means. This is the for loop statement for that particular code. And then after that, we will be we have started executing it now. So you'll go ahead with this. Okay. Yeah, from here. So for I equal to 0, I less than n, I plus plus. I think you understood the value of n is 4. Now for k equal to I plus 1. So we have to compare first. As I told you, we had P0, P1, P2, P3, right? And we have to compare first. So 6, 8, 7, 3 is a burst time. Now we need to compare first these processes and we need to determine which one is the shortest. By looking at based upon our analysis on common sense and intelligence, we can say just the process P3 is having the smallest burst time. But what about the other processes? They will not be knowing it. No, I mean, the computer might not be knowing it. So we need to program it. So for that, we have written this particular logic that for k equal to I plus 1. So initial will start with 0. 0 means the first process. Now this process will be compared with all these processes. So for k equal to I plus 1. So that is nothing but k is equal to how much now? 1. So 1 to 4 less than n. So 1 to 3 we are going to compare. So 1, 2, 3. So this process will be compared with this processes. Now, if the burst time of I, what is I here initially? 0, right? Here it is 0. So if the burst time of a process 0 is greater than the burst time of the process k is nothing but 1. So 0 and 1 are nothing but this is process P0, this is process P1. So what is the burst time of the process P0 here? 6. If 6 is greater than the burst time of a process P1, 8. condition failed. You can see here. You're seeing this. This condition has failed because the process P0 is having a lower burst time when compared to process P1. So immediately this particular loop will be terminated. Again, it will go back here to for loop, not the first one, inner loop. Now the value of k will become k plus plus. So now the value of k is equal to how much? 2. So now the process now again we'll be comparing. See, the initial value of I is 0 only now. Now the burst time of 0, the process 0 is greater than the burst time of process 2. So here the process. So we are comparing this process P0 with P1. This value does not satisfy. Now we are checking with P2. Now 6 is greater than 7. Now what we are doing here is 6 is greater than 7, but this condition is also failing. So this loop, this inner loop, we will not, I mean this inner body, we are not going to execute it. We'll again come back to this particular for loop. Now again it will get incremented. Now the value of k will become how much? 3, right? Because here 2, now it has become 3. What about the value of I? Still we are in the location 0. Now we'll again compare if bt of 0 is greater than the burst time of the process P3. So what is the process P3 we have here? 3. So 6 is greater than 3. Now the condition has satisfied. You can see here now the condition has been satisfied. 6 is greater than 3. So what need to be done? We will simply swap it. What we are doing here is we are simply trying to swap that particular variable. Temp equal to burst of I, burst of equal to bt of k. So what we are doing is in this position I am bringing P3. And in this position I am placing P0. So now what is the burst time here for P3? 3. What about just 6? P1, P2. This is 8. This is 7. So after completion of inner loop completely with the value with the first process P0, I got this statement. Now what will happen? This is completed. Now we will go to the outer loop here. Now the value of 5 will become here something like 1. I hope you people are getting it. So here the outer loop, what we are going to get right now is 1. So, okay, let me erase this too. Now the value of I in this case is 1. So same process will repeat. So I equal to 1. Now here k is equal to 2. Because we got the smallest one, so we don't have to compare with this. Now we have to compare these three. So now we are going to 1. So we are going to compare the process P1 with the remaining 2. So what is the value of k equal to 2? Now the burst time of the process 1 is greater than the burst time of the process 2. So what is the process 1 burst time? 8. 8 is greater than 7. Oh, condition satisfied. Immediately you will enter into this particular and you will simply swap it up. Now what will happen? P3 equal to 3, P2 equal to 7, P1 equal to 8, P0 equal to 6. Okay. Now again this process will be repeated, and when we are repeating this particular process, finally what is the value? What we are exactly doing is P3 equal to 3, P2 equal to P0 equal to 6, P2 equal to 7, and finally P1 equal to 8. So this is what we are going to get. And then we will be performing the operations. That operation is similar to your first program FCFS. If you see here the code, sorry, if you see here the code here, now we are going to execute this code. This code is common. We simply what we did exactly here is nothing but we first swapped them in a ascending order 3, 6, 7, 8, and then we are started working. If you see here this logic, whatever the logic is there, this is same as the logic what you have from here. See, WTO, WTO, WTI minus 1 plus BTO 5 minus 1. Same thing we are writing here. See? Yeah. And once this is done, you got the information. Now the remaining code is same as your FCFS. That is nothing but so process, burst time, waiting time, turnaround time. So I equal to 0, I less than n, I plus plus. So you're simply executing this. So average waiting time is W average waiting time n in this. Let me execute it and show it so that we can see how much what we are going to get here in this particular thing. So F11. Hmm. So how many processes we gave exactly here is 4 processes. Now the burst time for the process, how much we gave for the process, let me see it once so that we don't get any confusion. So we give it as burst time is okay. This is priority. Okay. So I gave it 6873. Let me give it 6. Enter the burst time of the process 8, 7, 3. So if you see here, did you see this? Okay, let me expand it so that you can get a clear idea here. See here. What did I do? The process P3021. This is what we are exactly doing it here. So that's what we have did it here in this particular thing. So then what happened? 3, 6, 7. Let's see. As I told you, we are going to arrange them in ascending order from small to big. We have arranged it, and based on that, we got this particular values. Let's check whether we got the same values or not. 7 milliseconds and 13 milliseconds. 31690. So the waiting time is 31690. So that is nothing but for the process P03, process P116. 316.9 is for process P2 and P3 got 0. See, you got the right output here. And same way you got this one. So P0 you got something like 9, P1 you got 24, P3 you got 3 milliseconds, and P2 finally, I mean, this one we got is 16. So based on that, what is the average waiting time we got here is 7 milliseconds, and average turnaround time is 13 milliseconds. So I think this is what we have got it, right? Yeah, exactly. 7 milliseconds, 13 milliseconds. So your output is perfect. So how much time it has taken to execute the entire thing? 42.16 seconds is has taken in order to execute this particular program. Okay, I hope it's very clear. This is very easy. Only thing we have to arrange an ascending order based upon the burst time given and simply perform the logic what is there in your first come first serve outputs. This logic. This is what we have did. That's it, nothing else. But before that, in this particular SGF, we arranged them. This is a code for arranging in a ascending order based upon the burst times given. That I think you people are very familiar with C programming and arranging the elements in ascending and descending orders. So based on that, we did it. That's it. This is what comes under your shortest job first. And then we have something called round robin. Oh, this is very easy. This is the most favorite and mostly used in many of the operating systems what we know about here. Now for this, what we are going to do, let me explain it. So round robin scheduling, what exactly the output we have taken 2433 and the time slice is 4. Cool. Let me explain it. Let me take a new page. Yeah. So here in round robin, what we are going to do is so in round robin algorithm, it's very easy. So here we have taken some 3 processes. P1. So for the process P1, we have 24 milliseconds. For the process P2, we have 3 milliseconds and 3 milliseconds. And in round robin, you will be given a time slice here. Time slice is nothing but the slots for individual process. So it is something around 4 milliseconds we have taken. 4 milliseconds means every process will get 4 milliseconds of slot, and within that it has to try to complete. Please understand this perfectly, because in this we have to do some little minor changes. Yeah. So every slot will be of 4 millisecond slot, means whatever you're drawing it should be of equal size. It should be of equal size. No variations in the shapes. I hope you're getting it like this. So we start from 0. So first, which process came, we'll give it process P1. Okay, process P1 is allocated. How much time it requires in order to execute? 24 milliseconds. But this slot, this entire slot is only for 4 milliseconds. Means the process P1 can do only 4 milliseconds task of work. So let me write it here. P1, P2, P3, 24, 3, 3. Now process P1 is allocated. He has completed 4 milliseconds time of task. What about the remaining? Still 20 millisecond task is pending. Pending here. Then came P2. I have allocated P2, but unfortunately P2 requires only 3 milliseconds. But how much is the slot we are giving P2? Since he completes the work 1 millisecond before than the slot what we are giving, he'll simply complete it in 3 milliseconds. 4 plus 3 is 7, and he will come out. What is the pending time this particular process requires? Nil. Then comes process P3. So why I'm allocating the process P3. Now, what is the slot we are given here? It's for 4 milliseconds. But how much he requires? 3 milliseconds. So he will also complete the work in 3 milliseconds and he will come out. So the pending is 0. So 7 plus 3 is 10 milliseconds. Now the only thing left is P1. Now you can say, sir, why don't we allocate P1? Because we don't have any other process now. We'll allocate directly 20 milliseconds to the process P1. Well, we can't do that. That's what we call the protocol of round robin. We have to give in slots only. So here what happens directly? Again, P1 is allocated, but when you're allocating P1 here, so 4 milliseconds task only he can complete it. So 10 plus 4 is 14. Still, how much work is pending? 20 minus 4, 16. Now again, since no other process is there, I'm allocating P1. So 16 minus 14, how much it will be? 12, I guess. Then since we don't have any other process now, you can say again, give 14 plus 4 is 18. So 20 minus 4, you're getting 8. Then again, you're getting P1, 18 plus 4 is 22. So this becomes 24. Again, you're giving P1, so 26, then becomes 0. Did I miss something? I guess I have missed it. 1, 2, 3, 4, 5. So 5 fours, 20. Okay, I have taken 4 milliseconds now. Fine. So 20. Just okay. Okay. Is it clear till here? I hope. So based on this, you people have to do it. Now, what is the waiting time? Since all the process has arrived at time interval 0, I don't have to subtract it because minus 0 will get the actual value. So the waiting time of the process P1 is how much? Waiting time for the process P2 is how much? And waiting time for the process P3 is how much? Now here in this case, if you look at it, you will be getting confused that, okay, there are so many P1s are available here. P1, 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 P1 here. Okay, so which one we need to consider means consider the last P1 which has arrived. That is nothing but this one. So on the left hand, whatever you're having, you take that. So 22 minus arrival time. What is the arrival time we have? 0 milliseconds, as I told you, minus the number of time it has executed previously. How many times it has executed, that we have to subtract it. So P1 has executed how many times before this P1? This is 1, 2, 3, and this is 4. So total 4 times it has executed previously. So 4 fours are every slot is of how many chance? 4 now. So 4 4 16. So 22 minus 16. 16 plus 4, how much? 20, 4 plus 6. So it will be 6. So it will be 6. Then you come to the process P2. Here it is the process. On the left side, what we are having? 4. What is the arrival time we have here? 0 milliseconds. All the process has come. So 4 minus 0. Minus, did it execute previously anything? No, this is the first time it has come up. So we don't have to do anything like this. So 4 minus 0 is 4. And then coming to the process P3, left side, what we have? 7. The arrival time is 0. Did it execute previously? No, this is the first time it executed and it has performed. So 7 minus 0 is 7. So what is the average waiting time we have got here? 6 plus 4 plus 7 by 3. 17 by 3. So 17 by 3 means how much you're going to get? 17 by 3. 5.66. So 5.66. What about the turnaround time? Same way. Turnaround time. So turnaround time for P1. So this one we will not be considering arrival time. Right side, whatever the value is there. So if we talk about P1, this is the last. Opposite we have 26. So 26 milliseconds. What about P2? Right side 7. 7 milliseconds. Then P3, P3, 10. So 10 milliseconds. So average is 26 plus 7 plus 10 by 3. So if you look at here, 26 plus 7 plus 10 by 3. So it's around 14.33. 14.33. So let's see whether we got the same or not. Twenty-four three times less is 30. Okay, so this is the way you got it. Okay, we got 5.6s and 15.6s. So as I was telling you, there was some mistake somewhere. So what exactly happened? Let's see. So 0 to 4 one time, 2 time, 3 time, 4 time, 5 times. So 5 fours are 20. So okay, cool. I got it. So we actually did here only till 20 milliseconds time. So if you see here, let me erase it and explain it. If you remove this, okay. See here, how many times we executed first time, second time, third time, fourth time, right? And then this should be a fifth time. So it is 0 to 4, 4 plus 3, 7, 7 plus 3, 10, 14, 18. Then we have 26, right? 24, 22, and then 26. Okay, so 1, 2, 3, 4, 5. So 5 fours are how many 5 times we have executed, but what is the total time we have? 24. So you have to execute one more time here. So this will become P1. That's what the small minor change we need to do here. So 6 4 6 are 24. Now exactly it has completed. Now based on that, the values will change here. This is something like 30. I mean 26. 26 minus 0 minus 16. So this will become 0, 10. Okay, let me write it again here. So waiting time for the process P1 is how much? So P1 has executed 6 years. So left side is 26. So 26 minus how many times it has executed previously? This is first time, second time, third time, fourth time, fifth time. So 5 fours are 20. What is the arrival time here? 0. So this is 6 milliseconds. Then what we have is something for the P2. P2 will be same. So 4 minus 0, that is 4 milliseconds. P3 will be 7 minus 0 because it did not execute previously. So it is one time, 7 millisecond. Arrival time is 0. So here something like 6 plus 4 plus 7. So how much we got is 5.6. And I guess that is what we got here, 5.667. But the average the turnaround time has been changed here. So the turnaround time will be here, something like 30 milliseconds. Remaining three will be same. So here it will be 30. So 30 plus 7 plus 10. 30 plus 7 plus 10. So it is 15.667. So you can write it as 15 point. So you can write it as 15.67 seconds. And that is what the program what we have got here, 15.67. Since it is a floating point, now 6 digits will be represented here. So it is written as 5, 6 and 1, 7. So let's execute this. Here is a program, very simple program, but only thing we'll be adding some logic here. Now this logic is something we are adding extra. So in this, what we are going to do is, since we had to see the burst time and all, for that we have written this particular logic for equals or less than. If max is less than, so we are allocating some max value, time slice here. Max is less than, so max value how much we are allocating here is nothing but whatever the burst time we are giving, we are considering it as burst max. And based on that, we are comparing if max is less than burst time, max equal to burst time. That is nothing but if what is the maximum value we are giving for each time slice, that is what he is taking it here. And based on that, it is executing it. And here in this particular scenario, in the this logic, the actual performance is actually taking place. What performance is taking place? That we have to reduce the values. Like for the process P1, initially it is 24. So when we started initially is 24. My process P1 is allocated 4. After that, what is how much amount of time is left here? 24, 20 milliseconds time is left. So that has to be allocated. So P1, P2, P3. So P1 is allocated 7, P2 is allocated 10. So that information will be stored and it will be executed. So how much time process P2 remaining is 20. That information is stored in this particular burst time here. Okay, and if this condition is not perfect, then we will be applying this particular condition and then we'll be executing it. Once this is completed, we'll get a Gantt chart like this in this format. And then we'll be getting the actual output. So this is what we are doing, average waiting time and turn. For this we are doing it. And finally the average waiting time we are doing it here, and average turnaround time we are trying to determine by n. And simply we'll be able to execute it. Let's see what is the output we are going to get. Compile and run. So how many processes? 3 processes. 24, 3, 3. Time slices 4. Say I think if people got the same output what we require, 5.667 and 15.667. But if you look at it, it has taken some time more when compared to the previous. Like in the previous one, that is nothing but SJF, it has taken around some 4.52 seconds. But here this one has taken 7.223 because it has to shift, because every slot is only for 4 milliseconds. It has to shift. Even though single process allocated multiple times, still we are giving it in a format of slots. That's a reason it has taken more time and compared to the other scheduling algorithms. Like FCFS, we have seen that 2.3 milliseconds completed. SJF, it has to do some comparison 7. I mean 4.5. Now round robin, if you talk about here, 7.223 milliseconds time it is taking. Sorry, seconds time it is taking to execute. The same way we can do it priority also. Priority is nothing but we will be allocated priority here, and based on the priority we will be executing our program. That's it. So for the priority, if you look at here, priority what we are giving here, so priority what we are giving is 1 2 3 4 5. The priorities we are giving, burst time is 1 5 10 2 1. Okay, so let's execute and see. So how many processes we are giving here? Total 5 processes we are giving. So total 5 processes we are actually giving here. Okay, now enter the burst time for the process 0. I'm giving it as 10. So what is the process priority for the process 3? Then for the process P1, the priority is 1. For the process 2, the priority is 4. And the burst time for the process P3 is 1 and the priority is 5. And for the 4, we are giving as 5 and 2. So if I look at here, you'll get the same output here. What is the average waiting time you received is 8.2, and whereas coming to the average turnaround time you received is 11.8. So did you see here? But what I want you people to concentrate here, if you look at, since we are comparing the priority and based on that we are executing it, can you see the process, how much time it has taken? 36.02 seconds in order to execute. So it has taken much more higher, because based on the priority we have to compare and we have to allocate the processes. It has taken more number of time to execute. And remember, it will not be in hours and all, it will be in seconds and milliseconds. That's it. So it has taken around 36.02 seconds in order to execute. What about the previous one? We have done it. That is nothing but your round robin. How much we got here? It's around, I think, 7.2 seconds. But here we got 36.2 seconds in order to execute the priority scheduling. So these are the 4 programs that are present in your first schedule. So I hope people have understood watching it. Fine, let me stop it. Thank you for watching.